Hi, I'm Prof L and welcome to Chemistry Matters, and today we're going to be talking about arrows. You might think, what have arrows got to do with chemistry? Well, in organic chemistry particularly, arrows are really important, and we are going to spend this video talking about them because the correct use of arrows will help you enormously when it comes to drawing mechanisms in your organic chemistry course, which is the fundamental, or one of the fundamentals of a lot of organic chemistry, is, as they call them, pushing arrows. Okay, so let's talk about arrows. But before we talk about arrows, we need to talk about reaction mechanisms. Okay, one of the goals of chemistry, and of chemists in particular, is to understand what the heck is going on in that beaker or test tube or round bottom flask that you just mixed two reactants in. Why is the reaction going? How is the reaction occurring? Why is the reaction not occurring? Okay, all of these questions can be answered if we can understand what is going on the molecular scale in a chemical reaction. And how do we understand that? Well, if you watch the kinetics videos a few videos ago, that's what we do. We carry out kinetic measurements, and from that we are able to get a very good idea of what's happening on the molecular scale. Now, in order to get a chemical reaction occurring, what do you need? Well, you need generally two things. You need bond making and you need bond breaking. That's pretty much it. And that's what we as chemists are trying to do. We are trying to figure out the series of simplest possible steps, simplest possible chemical processes that give us the product that we want. And those simplest possible chemical processes that we're talking about are, as I said, bond making and bond breaking. Now, how do we depict those processes that are occurring on the molecular scale on a piece of paper or on a whiteboard or whatever? Well, what we're looking at, as I say, is the making of bonds and the breaking of bonds. What does that involve? That involves electrons. That involves the movement of electrons, okay? And chemistry, definitely organic chemistry anyway, is the science of electrons, because electrons are the things that hold molecules together, okay? And organic chemistry is all about molecules. And so if we're converting one molecule into another, we're going to have a series of processes involving the making of bonds and the breaking of bonds, and then chemists depict that in a certain way in our three-dimensional land, I guess, okay? So let's take a look at these arrows. Right, so here is a mechanistic arrow. Well, that's just an arrow. It could also be a mechanistic arrow. And this is a very particular meaning in organic chemistry. And what it shows, what this depicts, is the movement of a pair of electrons. Okay? And the electrons are traveling from, the electron pair is traveling from the tail of the arrow to the head of the arrow. And you might think, well, that's pretty obvious. Not necessarily, it's not. Believe you me, I've seen some interesting arrows in my time, okay? But quite simply, that's what a mechanistic arrow shows, okay? Now, a two-headed mechanistic arrow, okay? And by two-headed, we mean that we've got the full arrowhead there, okay? That shows the movement of a pair of electrons. If we have just a one barbed arrow, as it were, then that would be showing the movement of a single electron. Okay, so that is, I guess, one of the differences that you can possibly have with mechanistic arrows. You can get the movement of a single electron with a one barbed head. With a two barbed head, that means that you're looking at the movement of a pair of electrons. Okay, and the movement of the pair of electrons is from the tail to the head. Right, let's have a look at a simple example. Here is a molecule of HCl. Okay, Now, here we're going to illustrate the use of arrows in in the first process that we're going to be looking at, and this process is going to be bond breaking. Okay, the use of mechanistic arrows to depict the breaking of a chemical bond. Right, we've got a covalent bond between the hydrogen and the chlorine. We've got 2 electrons in here. That's what a single bond is, essentially, isn't it? A single bond is comprised of 2 electrons. So we're going to break this bond, and in breaking this bond, what we're going to do is we're going to be taking this pair of electrons and we are going to be giving them to, or giving that pair of electrons to the chlorine atom, okay, to form chloride. So we start off, and this is really important, you start the arrow in the middle of the bond, okay, and you move the arrow to the chlorine like that. Okay, so we've got our full arrowhead there, the 2 barbed arrowhead. And if we carry out that particular process, then the products of that particular process are going to be H plus and Cl minus. Okay, so there's a little mechanistic step that we've drawn for the breaking of a single bond. Okay, so just to recap, we are taking that electron pair out of this bond and we are giving that electron pair to chlorine to make chloride, okay? And when we do that, obviously we're leaving the hydrogen electron deficient, and so hydrogen ends up with a positive charge, the chlorine ends up with a negative charge. Okay, so now that's a bond breaking process, and when it comes to drawing mechanisms, you will be drawing the breaking of bonds an awful lot. So remember, when you're breaking a bond, the tail of the arrow starts halfway along the bond that you're breaking. Okay, the head of the arrow goes to wherever that pair of electrons is going to end up, generally on one particular atom. And that is going to have charge implications when that happens. Because remember, these guys are quite happy at the moment. They're both formally neutral. Okay, their formal charges are 0. When we take that electron pair out of that bond and give it completely to chlorine, that's going to leave chlorine with a formal negative charge and H with a formal positive charge. So keep track of your charges whenever you are moving arrows around. That's very important. Okay, so that's the first process that we can depict using mechanistic arrows. So the second process that we can depict using mechanistic arrows is a bond making process. Okay, so let's, for example, say that we've got a situation like this. We've got a carbonyl group here, and we've got this oxygen that's got lone pairs on it, and we've got an H plus there, okay? And so we want to now make a bond between this oxygen and this H plus, okay? So how do we go about doing that? Using the mechanistic arrow, okay? So again, we remember that the mechanistic arrow is showing the movement of a pair of electrons. So how are we going to make that bond? What pair of electrons are we going to use to make that bond? Well, let's use this lone pair on oxygen here, okay? So we start the arrow from the source, I guess, of the electrons if you want. You finish the arrow on the atom or ion that you're going to form the bond to, okay? Pretty straightforward stuff, you would think. Okay, so what is the net result of that particular mechanistic process? It is going to end up looking like this, isn't it? Isn't it? Because we've done that quite happily. We have moved that pair of electrons, we've formed a bond between that oxygen, that hydrogen, or that H plus, using the pair of electrons, and we're all fine, aren't we? No, we're not. Not quite. Because remember I said that when you're moving electrons or electron pairs, that has charge implications. So remember, the formal charge on this oxygen before we start this is 0. It's quite happy. It wants 6 electrons. It's got a share of 6 electrons, okay? This H plus, It's a proton, it's floating around, it's got no electrons. We are formally going to be giving it one more electron, okay? And that is going to neutralize that H plus to just a normal bog standard hydrogen. So that's okay, but remember, charge is always conserved in chemical reactions, okay? Take the sum of the charges on those two reactants is 1 plus. So therefore the product has got to have a total charge of 1 plus along the line somewhere as well. We've drawn it like this with no charge. We need to look carefully at what is happening here, okay? This oxygen we said was quite happy, okay? It's got a formal charge of 0. What is happening when we take that electron pair, the oxygen still owns one of the electrons in that pair that we're forming the bond with, but it formally loses the other one to hydrogen. And so essentially, we're going from a situation where oxygen is very happy, formal charge of 0, we're essentially giving away one electron here, and so that is going to leave that oxygen with a positive charge. Okay, so that's one of the really important things in drawing reaction mechanisms, is making sure that you keep track of charge. Every electron pair that you move has charge implications. Okay, so just make sure that you're aware of that. Okay, whenever you carry out a mechanistic step, check your charges and make sure everything is okay. Right, so that's the second type of mechanistic process that we can depict using arrows. The third type is charge neutralization. Like so. Okay, so let's have a look at this particular molecule here. We have got CH3 and a CH3 and a CH3 and an H and an H and an H. Right, and if you were to go through and count the electrons in this, you would realize that that nitrogen has got a positive charge on it. Okay, so this nitrogen has a positive charge because it's got 4 bonds, okay? And so it's essentially given away one of its electrons to one of these hydrogens, okay? So remember, it wants 5 electrons, 2s2, 2p3 is nitrogen. It's really only got a share of 4 electrons there, okay? 1, 2, 3, 4. So, how do we neutralize that charge? We're going to neutralize the charge by losing H plus, okay? So let's lose H plus and see what happens. So how do we lose H plus? Right. Here is a mechanistic process I've seen written wrong many different ways. Okay. So what we want to do essentially is to take the electron pair and give in one of these NH bonds and give it to nitrogen, because that's the equivalent of giving the nitrogen one more electron. Remember, you've got 2 electrons here that are evenly shared. The nitrogen owns one of them, the hydrogen owns the other. If you are therefore breaking that bond and giving both of the electrons to nitrogen, the nitrogen essentially, formally gains 1 electron. The hydrogen formally loses 1 electron. So this is very similar to a bond breaking process. Very, very similar, okay? And so therefore we start halfway along the bond and we plop the electrons onto the atom where they're going to finish up, okay? And if we do that, then we then end up with this situation here, CH3 and CH3, etc., 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 CH3 plus H plus. That's the important bit. Remember, this overall has a positive charge, so therefore the product or products also have to have an overall positive charge. This guy is now neutral because nitrogen's got its lone pair back. It's lost H plus. We don't show the movement of the hydrogen. You never show the movement of atoms. You're always showing the movement only of electron pairs with these arrows, okay? So that's a charge neutralization process, Okay, so let's finish off this very, very brief video on mechanistic arrows by looking at this rather nice process here. Okay, so here we've got carbon, whoops, there we've got a carbon, and we've got an H, and we've got HH. We've got a Br, we've got a methyl, and we've got a methyl here. Okay, and this is now going to react with OH minus. OH minus is a base. Now, what do bases do? They like protons. Okay, bases like to react with protons. And so this OH minus, what is going to happen is that is going to come along and is going to take off this proton. And when it does that, we're going to see a whole series of things happening in this molecule, and we're going to depict them with mechanistic arrows. So the first process that we're going to look at is OH minus. We're going to form a bond between this hydrogen and this oxygen, okay? Because this is a very, very strong base. It's going to turn this into water. So we're going to remove this as H+. In other words, we're going to be breaking this bond here. So where is that electron pair going to go? Well, normally we would say it would go on the carbon, but that would give the carbon too many electrons. So where it's going to go, and you hadn't seen this before, it's going to go from the center of this bond to the center of that bond. It's going to make, in other words, a double bond here. Now, again, if you make a double bond here, then that carbon is going to have too many electrons, and so therefore it wants to lose some, and it can quite happily lose some by doing that, breaking this carbon-bromine bond and losing bromine as bromide. So this is a lovely concerted process. This is called an elimination. And those of you doing, again, advanced organic chemistry will learn about this. The product that you get from this is, right, we've lost one of these hydrogens off this bottom carbon. We've turned this single bond into a double bond, and we've lost the bromine. So we end up with this plus Br minus, okay? And not to forget a molecule of H2O as well, okay? So that's a lovely example of an intermolecular reaction followed by an intramolecular reaction. Very, very nice stuff. And you can show all that is happening in terms of these lovely mechanistic arrows. Right. So that's the basics of arrow pushing. Again, those of you who are going to go on and become organic chemists, and hopefully there's a few of you, will get very, very, very used to this, because you're if you go on to do a PhD, your PhD advisor will have sessions in which you look at mechanisms and you do all this arrow pushing and try and turn this reactant into this particular product, showing all the movements of electron pairs and stuff like that. So really important that you can get your head around this. And yeah, so I think that's it on arrows. And so thank you very, very much for your attention. And I will see you in the next video. Until then, take care and see you later.